My name is Abdelnasir from University of Khartoum in Sudan. My team and I would like to thank the organizers and Dr. Leila who connected us to this platform. And also I would like to thank the participants for showing. This talk is about short work we did with the COVID-19 task force in Sudan in order to understand the dynamic transmission in the country of the epidemic in the country, and a preprint manuscript about this talk can be found on ResearchGate under the same title. This is the agenda of talk. First, I introduce a brief description about the situation of COVID-19 in Sudan, and then I will present the model. I'll show you the result and also some simulating scenarios. And finally, we had a conclusion. It's going to be a very, very short presentation. Okay, COVID-19 in Sudan in numbers. The government of Sudan has officially confirmed the first case of COVID-19 in the country for a deceased man on 13th of March, and for a person who had a traveling history to the United Arab States. And then as today we have more than 8,000 confirmed cases, and which nearly half of them have been recovered, and we had more than 500 fatalities. And this number puts ranks Sudan as number 8 in the list of most affected country by the COVID-19 in Africa. This is the situation of COVID-19 in Sudan by numbers. And next question is, how our local government responded to this epidemic? So from the beginning of the virus confirmation in the country, the government of Sudan has suspended schools, universities, and also closed the borders, shut down the airport. And then after 10 days, as the cases get increases, the government of Sudan put in place a partial lockdown in terms of curfew from 6 p.m. to 6 a.m. Also, he allocated isolation centers across the country to host the COVID-19 patient. And after months, in 13th of April, we went in complete lockdown, except for the essential business. And so that lockdown is in place since 13th of April. And on 8th of May, we reached 1,000 confirmed cases, and by end of May, we had more than 5,000 confirmed cases. And the daily confirmed cases is in a steady step rising every day. As we see here, the government of Sudan took a gradual approach in response to this epidemic. They just placed a series of measurements as the cases get increases more and more. But there is no clear strategy to how to deal with this epidemic. We don't know when we're gonna get the herd immunity, or even the reopening and the reassumption day of the country is not clear. They keep changing and updating and extending the reopening day. For more than 3 times they did the extension. And we know that all evidence from our society indicates that there are far number of undetected cases. That because we have very, very limited testing capacity, as we had less than 15,000 tested since the beginning of this outbreak. And also our health system is also very, very, very fragile. It has been ruined over the 30 years in the previous regime, and the health sector has been greatly neglected and also was subject to numerous accounts of corruption, and mismanagement. So, and plus also we have public hesitancy to report, and there's stigmas uh, around this disease. People, okay, they don't like to report for the authorities, and also we had some denial attitude has been exaggerated through social media and some religious figures for politically motivated reason. So for these and others, it make harder for people come forward and report for the authorities. This is the situation of COVID-19 in Sudan and how the government plan to respond for this outbreak. So as a part of COVID-19 task force here, we as a mathematicians, okay, participated in studying this epidemic outbreak, and we have like three main concrete objectives. The first one, we want to quantify the effect of the government action in reducing the number of infections. The objective from this, the aim from the government restriction is to reduce and stop the virus from widespread community transmission. We want to quantify them in numbers, how the level of their impact. And also we want to estimate the case detection ratio. For now, we have like 8,000 detected cases. We want to estimate the percentage of these cases, of these detected cases against the undetected cases, which give us a clue of how the virus is widely spread in our community. And also, but we want to study the force of evolution and the dynamic transmission, which is unique to our country. This is our three main objective in this study. Okay, in order to attain these three objective, we adopted a kind of susceptible exposed infectious modified framework, SEI modified framework, but here we added an extra class. So we have the susceptible class, a susceptible person will acquire infection by force of lambda, and then by force of infection by rate lambda, and then move to the exposed classes E, where he spent the incubation period sigma, and then move to as become infectious. In the beginning, we consider as undetected infectious, IU, and then the authority will detect the undetected cases by rate alpha. And then the 1 minus alpha will remain undetected. And both the detected and undetected cases either will recover or die respectively with the different rates. So we expect that the recovery rate for the undetected and the detected one might be different, and the same argument for the death rate. Here alpha is the detecting ratio of detecting cases, case detection ratio. It has value between 0 and 1. If alpha is 0, we had no detected cases. And if alpha is 1, that means we detected all the infectious cases. And it's hard for alpha to be on the extreme limit at the end. It shouldn't be 0 and shouldn't be 1. And the intermediate value of alpha between 0 and 1 give us the ratio of the detected cases to the undetected cases. Okay, and alpha involve like many factors contribute to the value of alpha, level of public reporting, and also our testing capacity in the country. All of them like contribute to the value of alpha. Okay, then we translate the main diagram of the model here into system of ODE equation. Okay, subject to non-negative initial condition for all the 4 compartments we had in the system. Now I want to talk about the force of infection. The force of infection is coming from either beta 1, which is the effective contact rate for the undetected cases, plus Beta 2 for the effective contact rate for the detected cases. We scale all of them by the number of total population in the country, and we multiply it by factor 1 minus theta. Here, theta is a hyperparameter that account for the impact of the government measurement in reducing the number of effects. So if theta is, and it has value between 0 and 1, theta equals 0 corresponds to the absence of any intervention. And then we have the normal force of infection. And if theta is 1, that means it's a fully controlled situation, which is an ideal situation, hardly to attain. For example, earlier studies claim that Chinese government has a control of like 0.84%, which is very, very, very restrict, okay, measurement, which helps the Chinese government to, okay, to control the situation in the beginning in the beginning of this outbreak in Wuhan. But here we don't know for our country, and we want to estimate this. An intermediate value of theta between 0 and 1 quantifies the level of our government action. So R naught, which is a basic, okay, ingredient in epidemiology, it corresponds to the number of the secondary infections produced by the ferret by an individual infection, which is called R naught, basic reproduction number. It has this formula. We compute it using the next generation matrix approach. It's elementary calculation in mathematical biology. It has this formula in equation 3. Okay, now if we know the values of these parameters, the 9 parameters in this model, we can estimate the number of we can estimate the dynamic transmission and also the course of evolution of the of this outbreak, of this epidemic outbreak in our society. And the key is how to find their values. Okay, for example, we don't, instead of relying on internationally estimated value for these parameters, we want to estimate them using our local data, our locally confirmed data. And this is because for many reasons, first, the theta and alpha should be unique to our country. We know this. The testing ratio in our country should be different from the other countries. It depends on how much effort you put in fighting this epidemic. And theta also is the level of restriction. It's not just you announce the restriction, how many percentage of your population comply with the health guidelines given by the authorities, and how much they effectively have been executed. Because theta and alpha is uniquely to the country. Plus also the force of infection, effective contact rate for each community for any epidemic should be differ from the other communities. These are unique to our cultural norm and social behavior. For example, how do we carry out our prayers, or even, and how do you organize our religious meeting and for our ritual? How do we do our wedding? How do we celebrate? Okay, and how do we do our funeral? All this is part of our culture and social behavior, which is different from one society to another. This is the beta 1 and beta 2, alpha and theta, we think is completely unique for our society, and we can't rely on the internationally estimated value. And plus the recovery rate and the death rate and incubation period, this it shouldn't be greatly different from other communities, because this is unique characteristic for these diseases. But there are wide range variation, okay, for just so far estimated produced model for COVID-19. These values, they have wide range variation, and we cannot take okay, we cannot pick one from another. So it's better for us to estimate them from our local data. Thus, we don't want to take any constant values. We want to estimate them all uh, from our local data. Okay, and we did that by fitting the model and let them fit the model to the community confirmed number of cases, which for us is the detected cases. We fit them again to learn the values of our parameters, and we use very basic and rudimentary algorithm, which is the least square fitting algorithm. And here you can see the red dot are the cumulative confirmed cases, and the blue one is the fitting line is having estimated through our model. It has a good fit. Okay, and this is the value we get it, and I just want to highlight that the main incubation, the average incubation period we get it is about 4 days, which is within the internationally estimated period for this disease, and which give us clues that our model, our estimation is accurate. And also the recovery rate, and the death rate we obtained it for the detected cases was very close to the detected for the recovery rate that you can calculate it by using the number of the confirmed infection and the number of the recovered confirmed cases. And the two things we emphasize in this study was the alpha, the case detection rate we found is very small. It's about 22%, and theta, the impact of the non-pharmaceutical interventions that taken by the government to reduce the number of infection is also very low. It's only 23%. Okay, and we also observed that the recovery rate for the undetected cases is lower than the recovery rate for the detected cases, while the death rate of the undetected cases was higher than the death rate of the detected cases. The R naught value corresponding, we computed using this parameter values, estimated parameter values was 2.5, which is it's in the lower range of the R naught value, internationally R naught value estimated for the COVID-19 thus far, indicating that disease is every infected person could give the disease for 2.5 persons, pass the disease in average for like 3 persons. And okay, having estimated the parameter values, now we can study the course of evolution of this epidemic in the society. For example, now we can project and predict the peak time and when this epidemic gonna eradicate or end in our society. If nothing happens and we continue with the current level of measurement and the current case detection ratio, we would reach the peak time in mid-July. Okay, the peak time is the same for both detected and undetected case by very large numbers. We will have more than 150,000 detected cases and nearly 400,000 undetected cases. This number is far exceeds the limited capacity of our fragile health system, and then thus we argue the authorities to come out with comprehensive strategies to first ensure that effective execution of this execution and implementation of so far taken measurement, and also they should increase their level of capacity. In doing so, they could flatten the curve and then they to match the to flatten the curve so that our fragile health system will be in place and working, rather than if things are continuing in this phase, our health system will collapse, and then we don't have uh, uh, any option uh, to give hospitalization for the detected cases. This is the first clue that we get going from the model, and then now we know our level of restriction. We can play with these parameters. What if we increase the level of the restriction or the non-pharmaceutical government intervention by 10%? Okay, and you could do this by many variants. You can mobilize more policing sources to stop people from going outside of their home for non-essential business. You place law and order. Plus, also you can make a oriented and targeted media campaign, okay, to demystify the myth around this virus. And also you hold accountable the people who deny or show denial attitude about this COVID-19, irrespectful for the family of who have lost their loved one, and you hold them accountable. So by doing so, there are many room of improvement, either in implementation or also you come out with more innovative way for this restriction. If you did so, the model tell us that you will drop almost, if just you increase by 10%, you almost nearly half of cases will be dropping. So for example, you will have by the peak time, you have like 75,000 cases, detected cases, and 175 and like 180 undetected cases. Okay, but the peak time will be on earlier August. And as we see here, the more restriction it will delay the peak period. And another scenario also is, what if we both increase the case detection ratio and the level of measurement by just 10%? Here, the case detection ratio, you can do it also many room to do this. For improvement, you can add more, you expand your testing capacity by creating new labs. The entire country has like 4 testing labs across, allocated in different regions of the country. But you can open, this is something within the range of the government. They could open new testing lab, and also they keep active contact tracing for the infected people. If you did so, it's also you have more improvement. You would have, okay, less than 160,000 undetected cases. But here you increase the number of your detected cases. For instead of having 75,000, you have like 83,000 cases, and the peak time will be the same. The case detection ratio wouldn't delay the increase in the case detection ratio, wouldn't increase or decrease the peak period. And the main major source of spreading the disease in the community is the undetected cases. If you have more detected cases, then you have good opportunity to control the spread of this dynamic. But if you have more undetected cases, which is unnoticed in the community, they continue to spread this infection. Plus these and other scenarios also, we can play more about what if you decrease this and maintain this factor and decrease it. All the other possible scenario also we had okay, we consider all these simulation cases, and you could find them on the preprint manuscript, as I alluded earlier in the introduction section. You can find them in the research guide. So I had come to conclusion. So one thing the model tells us that the current efforts are not enough to flatten the curve, so that there is a diverse and comprehensive measures are needed to improve the efficiency of the so thus far taken measurement, and also come up with innovative ways to to make the measurement more efficient. And the best way also to control the spread of this epidemic is in simultaneous increase of both the case detection ratio and the and the non-pharmaceutical action. Okay, the the here the scenario. The measurement will stop reduce the number of infections, and the case detection ratio, it will keep all the infected cases as in the detected category. So you have a lesser number of undetected cases in the community. So you sink the source of the uh, yeah, it's the source that spread the infection in the community. And another thing also, the control measurement delays the peak time, but lowers the number of all infections. Yeah, this is something to be considered. Okay, because the lockdown cannot continue forever. It has a very okay risky consequence for the poorest people in the community, especially for daily workers and informal traders, which and the economic situation of the country is not good. And thus, if you want to lift up this measurement, you should increase the level of testing, okay, so that you have less number of undetected cases in the society. Because lifting a measurement, control measurement, would accelerate the peak time, but we're gonna go by high number of infections, and subsequently you're gonna have higher number of fatalities and deaths in the in the country. And we are speaking for the limitations of this model. We are aware that it's a deterministic model. It's endow all the limitations that intrinsic to the deterministic dynamical model. For example, the biggest problem here is the problem of non-identifiability, because our solution is scheme, a numerical scheme to solve this problem would not survey the entire solution space, and that we might trap in one local minima, and because there might be infinitely many local minima, and we just report in one in terms of the parameter values we had it. But nonetheless, yeah, we are okay, confident enough that because now we get our uh, the estimated incubation period is in line with the previous studies, okay, and with the clinical trials. Plus also the recovery rate and the death rate also is very close to the actual uh, death rate and the recovery rate, which we can calculate it from the data. This gives us evidence that we are in the right local minimum, or we have the right solution. Okay. And but now we are considering an stochastic solution for this dynamic. A stochastic solution gives us the opportunity to survey the entire solution space, and then we get rid of the problem of non-identifiability, and we are doing so by using okay Bayesian approach method and use the Markov chain Monte Carlo okay algorithm to solve it, because Bayesian many prior information about the distribution of the parameters now we already know. At least we can have them from the literature, and then we can incorporate that in our model, and that the Bayesian framework allow us to do so. Another consideration also about the age restriction. Okay, we know that COVID-19 affect some part of population harder than the others. So we are considering an age structured version. Especially we want to uh, emphasize the elderly people who are affected mostly by the COVID-19. Also, some region, we were also considering a state level version of this model because some region of the country has been hit harder by COVID-19 than the others. So if we consider the regional uh, structure of the model, we could have a more accurate resolution. And thank you.